Welcome back. So today we're going to talk about one of the most foundational topics in differential geometry, and that's the geometry of curves. And you might think, well, what could there possibly be to know about curves? It sounds like a very simple subject. Actually, what we'll see today is that there's a lot of depth and a lot of richness in curves that you might not see or notice at first glance. And that by getting our head around some of these more interesting, complicated phenomena, we're really going to end up with a strong foothold for studying the rest of differential geometry. In fact, a lot of this course is focused on studying curves and surfaces. Why is that? Why so much attention to these cases? Well, for one thing, a lot of the geometry we encounter in our lives is well described by curves and surfaces. So curves might describe things like road networks or strands of hair or your signature when you go to sign for your credit card. Surfaces show up, of course, in every object that we look at or touch or feel, right? You might also say in our day-to-day lives, solids also show up, three-dimensional bodies. But if we want to describe the specific shape of a three-dimensional body in space, really there's not a whole lot more we have to say than what is the shape of its boundary, the surface along its boundary. Okay, so in general, differential geometry studies n-dimensional manifolds. And again, we're going to focus a lot on low dimensions, curves, which are intrinsically one-dimensional, surfaces that are two-dimensional, maybe a little bit about volumes, which are three-dimensional. Why do we do this? Well, again, because this is the kind of geometry that shows up in our everyday life. It's also the kind of geometry that shows up in a lot of applications. If we want to do geometric computing, we'll often be working with data that is one or two or three-dimensional. Okay, but that being said, I always have somebody in my course who comes to me and says, yeah, but come on. This is just baby stuff, curves and surfaces. Give me the real stuff. Give me the n-dimensional case now. And I really have to say to these people, low-dimensional manifolds are really not baby stuff, not even by a long shot. So there are problems in low-dimensional geometry and topology that are as hard or harder than anything you're going to find in higher dimensions. So just one example is in the one-dimensional case, there's a question of unknot recognition. If I give you some complicated closed loop in R3, right, some wound up curve, I want you to decide, I want you to compute and determine, is this curve equivalent to just the round circle, where equivalent means I can untangle it without having it pass through itself or without breaking it open. So any curve that can be turned into this round circle is called an unknot, otherwise it's called a knot. So a curve like this one, I can't untangle no matter how hard I try. Okay, so as of 2021, nobody knows what is the computational complexity of this problem. Right? Despite hammering away at this problem for many, many years, nobody can answer a problem as simple as, is this curve knotted or not? Okay. A grand challenge in the two-dimensional case is the Willmore conjecture. So the Willmore conjecture says, okay, for a surface of a given topology, what is the smoothest I could possibly make it? So if I have a genus 0 surface, something that has no holes or handles, then it turns out, it's actually not terribly hard to show, that the smoothest you can possibly do is you can turn it into the round sphere, like the unit sphere. Okay? And smoothness here means we have some particular energy that measures how much the surface is bent at every point. That's called the Willmore energy. Now, although it wasn't too hard to figure out that the round sphere is the minimizer of Willmore energy for genus 0, people worked very, very long and hard to figure out what really is the global minimizer of Willmore energy for genus 1, for a torus or a donut. And for a long time, there was this conjecture that it was probably this thing called the Clifford torus, which is just a torus with a certain ratio of radii. In fact, it's drawn right here. But it wasn't until just a few years ago that it was actually proved that this is the minimizer. And still, nobody knows for sure what is the minimal energy surface? What is the smoothest possible surface that you can make for genus 2 or genus 3 or higher genus? Right? So surprisingly hard problem. By the way, you might ask, why do you care, right? Why do you care what the smoothest surface is? And what this really has to do with is how do you visualize or how do you realize an abstract topological space? Right? All I know about my space is the number of holes or handles in it. What should I draw? What is the canonical representative of this topological space as some geometric surface? Okay, and this is very, very important idea, coming up with these canonical representatives, not only for mathematics and visualization, but also for computation. So a theme we'll see a lot in discrete differential geometry is that you can often map between two spaces by bringing them both into some canonical configuration. And minimizing curvature is one very powerful way to do that. In fact, this idea of minimizing curvature is deeply connected to a recent major breakthrough in three manifolds, which is the resolution of the so-called geometrization conjecture. So the geometrization conjecture kind of implies something called the Poincaré conjecture, which is one of 10 so-called Millennium Prizes, which are open questions for which if you solve it, you get $1 million. And so far, this Poincaré conjecture is the only one that's been solved by a mathematician named Perlman, and this made major news. So as far as I understand, this is the only mathematical breakthrough to ever have been featured on the cover of the journal Science, for instance. What does it say? Well, without going into too much detail, basically it says something like what we were talking about before. If I have a topological space, how do I describe it geometrically? And what the geometrization conjecture says is that there are actually kind of 8 sort of Lego building blocks, geometric Lego building blocks that I can kind of glue together to get any three manifold at all. So kind of an amazing and surprising way of classifying three manifolds so that we can start getting our heads around it, right? How do you prove any kind of theorem? Well, it's nice to have a taxonomy of the object that you're working with, okay? So hopefully this gives you a sense that, again, that low-dimensional manifolds are not baby stuff. Some of the most challenging questions in modern mathematics are about low-dimensional manifolds. The other reason for studying low-dimensional manifolds is that they give you a lot of intuition for higher dimensional manifolds. If you do really want to work in higher dimensions, well, guess what? A lot of the behavior that you have in n dimensions is not so different from what you see in 1, 2, and 3 dimensions. Conversely, in some applied fields where people like to toss around the term manifold, you might actually find less deep and interesting geometry than you might imagine. So in fields like data analysis and machine learning, at least today, you don't run into a whole lot of interesting structures like fiber bundles and Lie groups and curvature flows and spinners and symplectic structures. So hopefully you don't get too swept up in the hype about n manifolds. Okay. Moreover, why study low-dimensional geometry? Well, because curves and surfaces are beautiful. Not just aesthetically, but there's a lot of beautiful theory, beautiful observations you can make about curves and surfaces. And kind of surprisingly, a lot of the interesting structure of geometry and topology can sometimes evaporate when you go too high in dimension. So in some sense, if you have too many dimensions available, certain things become really easy to do. Certain rich structures don't exist anymore. Okay, so hopefully you get the sense that I'm really excited about telling you about curves and surfaces, and there's a lot of rich and beautiful stuff to know. So how can we talk about curves and surfaces? This is such an important topic that over the generations, people have come up with lots and lots of different ways, different languages to express the geometry of a curve or surface. So a very classic thing to do is to express the local geometry of a surface in terms of a height function over a tangent plane. We can write a surface as a local parameterization over, let's say, a piece of the plane. We can use what are called Christoffel symbols to explain some things about what are going on surfaces. We can use differential forms, as we've been doing so far in this class, and that's what we'll continue to do. This is a nice sort of coordinate-free way to work. There's a language of moving frames, which talks about surfaces as change in a frame, or a coordinate frame adapted to the surface, and this is actually not so disconnected from differential forms. And then there are complex descriptions, Riemann surfaces or quaternionic functions and so forth. And on. This is not a complete list. So people can get pretty religious about these different dialects. Depending on where they learned geometry from, who their teacher was, they might feel really strongly that you should really be using, Christoffel symbols, you should really be using Riemann surfaces or whatever. The reality is, just like in life, it's best to be multilingual. The more languages you speak, the more of these terms and ideas you understand, the more people you'll be able to communicate with, right? The more you'll be able to share knowledge and gain knowledge and create new and interesting things. Okay? So in this class, we're going to take a dive deeply into one description using differential forms, but we'll touch on these other ones occasionally to help a little bit with the translation. In the discrete case, there are also lots of different ways to represent geometry. So for instance, if we want to talk about a surface in space, we could think of that as, let's say, the zero set of a scalar function on a grid. So if I want to explain what this sphere looks like, I might have a function that vanishes on the sphere, is equal to 0 on the sphere, is negative inside and positive outside. Okay, this kind of implicit description is good for certain computational tasks. It's good if I, for instance, want to change the topology of my surface, allow it to split and merge. On the other hand, storing this implicit function, let's say on a grid, is really expensive. I have to store a lot of values. Adaptivity is hard if I want more resolution in one place than another, and it might become hard to solve sophisticated equations on the surface. There are ways to do this, but maybe not completely natural. A different way to encode geometry is to encode it explicitly. So rather than having this function that kind of says, okay, you can check if I'm on the surface or not, or if I'm inside or outside the surface, rather just kind of list points or elements where the surface lives. So the canonical example of this for us is a polygonal surface mesh. Right? I'm going to approximate the sphere with a bunch of triangles or other polygons. With this representation, changing topology is a bit harder. You can do it. There are ways to do it, but it's a little bit more painful. On the other hand, it's quite cheap to store these surfaces. You can get spatial adaptivity very easily, and so on. And in particular, there are much more mature tools for solving equations on surfaces. Okay? But just like when talking about smooth languages, the really important thing is to not be religious. Right? Don't say, explicit is better than implicit, or level set methods are better than mesh-based methods. No. Use the right tool for the job. Figure out what algorithmic task you're doing, what you care about, what quantities you care about, and pick the tool that makes the most sense. Okay? So, just a little bit of an overview of where we're going with our discussion of curves and surfaces. Our goal, ultimately, is to understand curves and surfaces from two complementary viewpoints, the smooth and the discrete. In the smooth setting, we are going to express our geometry in terms of differential forms, and we will think about this in terms of vector-valued differential forms. So remember, we generalized our whole long discussion of scalar differential forms into vector differential forms in this recent note. In the discrete setting, we're going to use a abstract mesh, like an abstract simplicial complex, as our domain, and we're going to describe the geometry of that abstract domain using, discrete differential forms, using values associated with the vertices and edges and faces of this abstract mesh. Why are we doing it this way? Why are we doing this in this somewhat unusual way of writing everything down in terms of differential forms and discrete differential forms? Well, the payoff is that once we've done this, it becomes very easy to switch back and forth between the smooth and the discrete setting. So if we wander into the library and we dust off an old book about surface theory and we find some strange and beautiful and interesting facts, it becomes very easy to plug those into our computer and say, we can do some new and interesting thing. We can really solve some algorithmic problem. Okay, that's where we want to go. But let's start at the very beginning and let's talk about smooth curves in the plane. Very classic topic. Okay, how do we describe a curve in the plane? Well, as we've discussed, there are lots of different ways to do it. I think one very natural perspective is to say, a curve is a subset of points in the plane. So this is, at least naively, kind of the perspective of algebraic geometry. I might have a function, and wherever that function is equal to 0, that's where my curve lives. So, simple example, a circle is the set of points, xy, where x squared plus y squared minus 1 is equal to 0. Right? Wherever this function vanishes, I find the circle, and okay, if I'm inside the circle, it's negative. If I'm outside, it's positive. This is fine, but becomes a little bit tricky when the curve crosses itself. So if we want to talk about the kind of quantities that we care about in differential geometry, like the tangent and the normal and the curvature and so forth, you can do it. There are techniques for dealing with these singularities, but it becomes a bit tricky. So in differential geometry, a very natural way to describe curves is in terms of a parameterization. So rather than thinking of the curve immediately as a subset of the plane, instead what I do is I start with a piece of the real line. I start with a straight piece of string, and I have a map that tells me how do I deform that piece of the real line into the plane to make a curve. Okay, so the image of that map, the points I end up with, of course, are still a subset of the plane, but somehow I have a little bit more information about what's going on. An example of a parameterization is, again, the circle. So I can write the circle as a map gamma of theta, which is equal to cosine theta sine theta, right? Something like this. And when we work with parameterizations, it becomes a lot easier to talk about crossings. If I want to understand the tangent or the normal or the curvatures, I can just restrict my map to one of the little pieces where the curve crosses itself, and I don't have any trouble. So we'll introduce some more precise language to talk about this situation of embedded versus immersed curves. Another nice thing about parameterizations is we can encode things like velocity, right? A curve is no longer just a subset of the plane, but is also something about how fast we're moving along the curve, right? Part of a parameterized curve is the parameterization, and this is both nice in some ways and causes headaches in others. If we're going to compare two curves by their parameterizations, we have to think about the fact that these are not always identical as functions. Okay, so we'll talk a little bit about that. Maybe most important for this course is that parameterized curves have a natural discrete analog that actually we're going to see in the next lecture, that we can work with polygonal curves as a discrete version of parameterized curves, and a lot of the things that we want to say about the differential geometry of smooth curves very naturally translate into this setting. Okay. To give a definition, a parameterized plane curve is a map taking each point in an interval 0 to L of the real line to some point in the plane. Right, so we have our interval. At each point, we know where it lands in the plane. If we know where all those points land, well, we get a whole curve. Okay. And we could also put conditions on this map. We could say that it's continuous, that it's differentiable, that it's smooth. Generally, we're going to assume that it's as differentiable as it needs to be in order to define the quantities we're going to define. Okay. Concrete example, again, we have the circle. Right? The circle can be described as a parameterized curve gamma that takes the interval 0 to 2 pi into the plane, right? By doing what? Well, taking any value s to cosine s sine s. This is also a good example of a closed curve, meaning a curve where the two endpoints meet up. Okay. Our next basic property of a curve is going to be its differential. So we're talking about differential geometry. How do we understand shape? How do we analyze it? Well, we do it by looking at derivatives. So if we think about a parameterized curve as an R2 valued zero form, okay, kind of a fancy thing to do, but all we're saying is on the interval of the real line, we stick in no vectors, we get out a point in the plane. Okay, you can think of that as a zero form if you like. Okay, if we do that, then the differential or the exterior derivative says how vectors on the domain get mapped or stretched into the plane. Right? So if we have our curve gamma and we take a little vector u on that interval, we could really think about picking up that interval and bending it into the blue curve and seeing what happens to that arrow. And depending on exactly how we bend the interval into that curve, we're going to get a vector of different length. Okay? The differential is the thing that's telling us how do we figure out that vector. Right? Given u, what is the vector in the plane? Well, it's d gamma of u. We take the vector and we kind of push it forward into the plane. Okay? The differential is, by the way, not the same as the tangent. Okay? The tangent, well, let's just talk about what this means intuitively. The tangent is a vector that just barely grazes the curve, okay, informally. Or more formally, the unit tangent is the map obtained by normalizing the first derivative of the curve. So we can write t of s at any point s along the curve. The unit tangent is the derivative of the curve with respect to its parameter s divided by the norm of that derivative. Okay. What is the difference between the tangent and the differential? Well, the tangent is a unit vector at each point of the curve. The differential is a thing that says if I have any vector defined on the domain, how do I stretch it out so that it's sitting on the curve, right? It's not a particular vector. In fact, it's not a vector at all. The differential is a map that takes vectors as input and produces vectors as output. Okay? We can, of course, still relate these two quantities by saying, well, the tangent can be expressed by taking a unit vector on the domain, DDS, right? Just the kind of basis vector along the s direction, applying the one form d gamma to it, so pushing this vector forward into the plane, and then normalizing it. That vector that was unit length might have gotten stretched out a bit, so we have to normalize it to make it unit length. Now, one very important thing to note is that, of course, we can't do this normalization if the denominator is 0, right? If the derivative of gamma with respect to s is 0, in other words, if the curve kind of slows to a stop, well, there's no way to normalize this vector to get a unit tangent. So often we'll make some simplifying assumptions about this map gamma just to make sure we don't run into these nasty cases. One simple assumption would be to say the derivative should never go to 0. We say that the curve is regular. An even stronger assumption is to say that the derivative has unit length at every point. So norm of the derivative of gamma with respect to s is equal to 1 everywhere. This is a nice assumption because then we can simplify all these expressions. We can just say, oh, the tangent really is just the derivative of the curve with respect to s. Or equivalently, we can say that if we take the unit vector field on the interval and push it forward by the differential, then we get the unit tangent. Lengths are preserved by the map gamma. Another word for this is to say that gamma is an isometry. It preserves distances between points on the curve. Okay? Concrete example, let's compute the unit tangent of a circle. So we have our favorite curve gamma that goes from the interval 0 to 2 pi by taking s to cosine s sine s. Okay, looks like this. Hopefully you know what a circle looks like. And what is the differential? Okay, we can compute this just in the usual way. We've been talking about the exterior derivative, the differential all along. Okay, well, we take the partial derivatives of each of the components, cosine s and sine s, with respect to s, and multiply by the basis one form ds. So we get minus sine s cos s times ds. Okay, so d gamma tells us how to take any vector in the interval and stretch it out into the plane. To get the tangent, we'll take the unit vector pointing in the right direction, partial s, and push it forward to get minus sine of s cosine of s. Okay, and then we need to normalize. We need to find the unit tangent. So what's the length of this vector? Well, it's cosine squared of s plus sine squared of s, which for any value of s is equal to 1, right? It's just a point on the unit circle. And so we actually don't have to do any normalization. The curve is already arc length parameterized, and we get t is equal to just d gamma of dds, or in other words, t is equal to minus sine s cos s. Okay, this is an intentionally boring example just to work through the basic mechanics. Okay. So let's talk a little bit more about this idea of parameterization. Right? What is really the consequence of expressing a curve as a map? Well, one way to think about this is in terms of reparameterization. So if we have a curve already, let's say gamma, we can reparameterize it, we can come up with another function that describes the same curve by first applying a map from the interval to itself. And then after we've mapped the interval to itself, we go into the plane using our original map gamma. So if eta is our map from the interval to itself, our new curve is gamma tilde, which we get by just applying gamma to eta. This all becomes a lot clearer if we draw some pictures. So let's say I have this curve gamma, and I've marked some points on the interval 0L that get mapped to points in the plane. What you notice here is that this is not an arc length parameterization, but at least a constant speed parameterization. I have equally spaced points on the interval, and those get mapped to equally spaced points on the curve. I can cook up another map, gamma tilde, that describes exactly the same curve, but is parameterized a different way, where I move faster and slower along this interval. So in particular, let's say I take the function eta of s on the right, that's mapping 0L to 0L, and I plug it into gamma, then I get something that looks just like gamma, but these dots are spaced out by different amounts. Why is that? Well, if you look at this curve on the right, at some moment it goes really fast, then really slow, then really fast again. Okay, so we have a different kind of velocity that we're traveling along the same curve. So the key idea is the new curve looks identical. It has the same image. It describes the same subset of the plane, even though the map describing it changes. And this is really fundamental to the idea of parameterized descriptions of geometry. There's additional information in your description beyond just the shape of the object that you're looking at. In some cases, this additional information can be really helpful. For instance, if it encodes something physically meaningful, like the velocity as you travel along the curve. In other cases, it can be really painful. I'm trying to compare two curves, and they have different parameterizations, even though they describe the same shape. Well, then I can't just check that the maps are equal to each other. By the way, this is ultimately why it's hard to compare two different meshes and say whether they have the same shape. A mesh is kind of a parameterization of a surface. And so if I just try to compare the meshes directly, to walk down the list of vertices and compare their locations, this is a really bad way to do it. The thing that's underlying this difficulty is the fact that I have two different parameterizations of this same geometry. This idea of reparameterization is also helpful for getting a deeper intuition about the differential. So what does the differential look like under reparameterization? In particular, let's say we have, again, a curve gamma tilde, which is obtained by composing our original curve gamma with a remapping of the interval over which the curve is defined. Okay? Then the differential, d gamma tilde, is likewise going to be just a composition of the differentials of those two maps. What does that mean? That's a lot of language to say something that is visually quite intuitive. If I start with this interval over which the curve is defined, and I reparameterize, well, what I'm going to be doing is stretching out that interval different amounts in different locations, and then mapping it into space. A vector that starts out on the original interval is going to get stretched twice. It's going to get stretched because I'm remapping the interval, and it's going to get stretched because I'm going from that interval into space. Okay? And we can also see from this picture how the differential is different from the unit tangent. It's not just capturing the grazing direction of the curve, but it's actually telling us something about the map itself. How much did this map stretch out the domain? Okay, and a really extreme case would be that the stretching goes to zero. Something really disastrous happens. And so again, something we often do when working with curves or other geometry is to make simplifying assumptions that make our life easier. With curves, the most basic assumption is to say that the parameterization is regular, meaning the differential is not equal to zero anywhere. We never slow down to zero. Another word for this is to say that the curve is immersed in the plane. Immersed sounds like a kind of colloquial term, but really it has a precise meaning. Right? To say that the curve is immersed means its differential is non-zero. Okay? Without this condition, a parameterized curve might look non-smooth, but actually be differentiable everywhere, or it might look smooth, but fail to have well-defined tangents. Right? So basically, if your curve is not regular, all bets are off. So for instance, here's a curve that looks like we have this corner where it shouldn't be differentiable, and yet because we're slowing down to zero and then starting back up again, it actually will turn out to be differentiable. Okay, we'll see that in a second. Here, on the other hand, is a curve that looks perfectly good. It's a nice round circle, right? But because we slow to zero, we don't have a well-defined differential everywhere, right? So a lot of painful things can happen if your curve is not regular. Okay, to look at this in a little more detail, let's consider the reparameterization of a piecewise linear curve. So gamma of s is equal to ss if s is less than or equal to 0, or s minus s if s is greater than 0. And we're going to consider a reparameterization eta that takes s to s cubed. So over the unit interval, this map will take 0, 1 to 0, 1. Okay. If we plug eta into s, we get a new curve, gamma tilde, which is equal to s cubed if s is less than or equal to 0, or s cubed minus s cubed if s is greater than 0. I've plotted the curve in the bottom left. Okay, so it is still piecewise linear in terms of its geometry. Right? We go up the left side, and then we make a steep turn, and we come down the right side. But actually, this curve is perfectly differentiable. You look at it and you think, that's not differentiable. It's got this sharp corner. No, it is differentiable. Why? Well, let's draw the two coordinate functions. Okay, so here they are. The first one is essentially the x component of gamma tilde. The second one is the y component of gamma tilde. And they look like perfectly nice functions. I could definitely tell you what the derivative of gamma tilde is at 0. Right? No trouble. Well, the problem is, even though I know what the derivative is, it happens to be 0. Right? It's 0, 0. So because the curve is not changing at all at this point, really we've slowed down to 0 when we hit that sharp corner, we still can't define what the tangent would be there. Right, so we come back to this idea that the tangent is not simply the derivative of the curve, it's the derivative of the curve divided by its norm. Okay, and because we can't define the tangent, we also can't define the normal, we can't define the curvature, or a lot of other quantities that we might care about, at least not in the classical sense. Right? We can't just do ordinary differentiation and hope that these quantities will come out. Okay? But the really important takeaway from this example is that differentiability doesn't mean nice, right? Just because your curve is differentiable doesn't mean it's a nice curve. You really want to ask for other stronger properties like, well, I would also like it to be regular. I'd also like that derivative to be non-zero everywhere. Okay. A different notion of nice that often comes up is the idea that your curve is embedded. So roughly speaking, embedded means that the curve does not cross itself. So good mental cartoon is this curve is embedded, this curve is not embedded. Okay. To give a more precise definition, a curve is embedded if it is a continuous and bijective map from its domain onto its image, and if the inverse of that map is also a continuous map. And it takes a minute to digest. It's helpful to have some examples. So, for instance, what would be an example of a continuous injective curve that is not embedded? Right? So it doesn't break or jump anywhere. It's 1-to-1. Every point in the interval gets mapped to a distinct point in the plane. So how could it be? How could it be that I have a nice continuous injective map, but I failed to be embedded? Isn't embedded something about crossing the same point twice? Well, this is a really, really important example. Actually, it's a little more subtle what embedded means. So here we have a half-open interval mapped to the circle in the usual way. Right? I map S to cosine S sine S. This is a continuous map from the interval to the circle. And it's injective. It's 1-to-1, right? For every point on the interval, I have a point in the plane. For every image point in the plane, there's only one point on the interval that got mapped to it. The problem is the inverse of this map is not continuous. If I try to take this nice closed circle and map it back to the interval, I have to break it open at a point. I have this sudden jump in the map from the circle to the interval as I pass around that white point on the right. Okay? So the real idea of an embedding, whether it's for curves or surfaces or whatever, is that an embedding preserves the topology of the shape. We're not going to be too precise about that here, but in this example, for instance, an embedding should take an open curve that has two endpoints to another open curve that has two endpoints. If you see an interval getting mapped to a closed curve, that can't be an embedding. Okay? What are some other basic quantities we can talk about on curves? Well, there's the normal. So the normal is informally a vector that kind of sticks straight out of the curve. More formally, when we're in the plane, we could say that the unit normal is just a quarter rotation of the unit tangent in the counterclockwise direction. So if we use script j to denote a quarter turn, then at any point s, the unit normal n of s is equal to j applied to t of s. Okay. In coordinates, by the way, a quarter turn can be easily achieved by just swapping the two components, x and y, and negating the first component. Why? Why does that work? Why does that represent a quarter turn? Well, okay, for one thing, you know that these two vectors, xy and minus yx, are orthogonal. If I take their dot product, I get x times minus y plus y times x, which is equal to 0. Okay, so they're at right angles. How do I know I went in the counterclockwise direction? Well, I could kind of take the cross product. Right? I could take the cross product of what I started with and what I ended up with, and I would see that that is positive, kind of sticking out of the plane. And so I know that that was a counterclockwise rotation. Okay. Let's see an example. Our favorite example of the circle. Again, gamma, which maps s to cosine s sine s. The tangent that we worked out before was minus sine s cos s. So what is the normal? Okay, you should be able to do this pretty easily. Well, you just swap the two components and negate the first one. So we get minus cosine s minus sine s. And I've drawn these normals as unit vectors. Right? And something funny happened. All the arrowheads point in. So you don't quite see that they're arrowheads, but they are a bunch of 8 arrowheads all around. We could, by the way, also adopt the convention that the normal points out, right? Why not say that n is minus jt? That's also a vector that sticks straight out of the curve in some way. Well, you could do that. There's absolutely nothing wrong with doing that. The only thing that you should make sure to do is stay consistent, right? If you defined the normal one way on one curve, define it the same way on another curve. Otherwise, you're going to get sign errors creeping into your calculations. An absolutely fundamental quantity associated with a curve is its curvature. So informally, curvature describes how much a curve bends. And so if I have this blue curve, then on the left part, I have very little curvature. I'm going pretty much straight. On the right part, the curve quickly turns, and so I have more curvature. How can we be more precise about this? Well, more formally, the curvature of an arc-length parameterized plane curve can be expressed as the rate of change in the tangent. So you can imagine if I'm really walking along this path and carrying an arrow that has to stay aligned with the path, the curvature is just how quickly I have to turn to keep this arrow aligned. Okay? And we can write this as the curvature, kappa of s, at any point s, is equal to the inner product of the unit normal at s with the derivative of the tangent at s. Okay, again, this is true only for an arc length parameterized curve. We could also write this, if this is arc length parameterized, as the inner product of the normal with the second derivative of the curve. So you get this feeling that curvature is something like a second derivative. That's an important idea in differential geometry. Another way we could think about this is to say, well, at each point of the curve, the tangent makes an angle theta with some reference direction, like the horizontal direction. Okay? In that case, the curvature kappa is just the derivative of this angle theta with respect to arc length. A third and completely equivalent way of defining curvature is using the osculating circle. So roughly speaking, the osculating circle is the one that best approximates the curve at a given point. You can imagine we tried out every possible circle, and we stuck with the one that looked the most like the curve. More precisely, to define the osculating circle at any given point P, we can consider two other points, one to the left, one to the right, both at the same distance along the curve from P. And there will be a unique circle passing through those 3 points in the plane. If we then let these points get closer and closer and closer to P, we're going to get a sequence of circles that pass through those points that get closer and closer and closer to the osculating circle. So the osculating circle is the limit of this process. The curvature of the curve at P is then just the reciprocal of the radius of the osculating circle. Kappa of P is equal to 1 over r of P. Does this definition agree with our intuition about how curvature behaves? Well, hopefully it does. So if we have a curve that turns around very quickly, we need a very small circle to approximate that rapid turning around. Right? Or if we have a curve that just gently bends, we need a very large circle to capture that gentle bending motion. Okay? So lots of different ways of talking about curvature. Why is it so important? Well, one reason is the fundamental theorem of plane curves. Right? So just like we had the fundamental theorem of calculus, we have a fundamental theorem for curves, and what it says is that up to rigid motions, an arc-length parameterized plane curve is uniquely determined by its curvature. Okay, so if you only tell me the curvature function of the curve, you don't tell me any points on the curve or any of its tangents or any other data, just the curvature function, I should be able to recover the shape of the curve up to a translation and rotation in the plane. Okay. Why is that true? What's the intuition? Well, hopefully you've gotten a sense by now that curvature kind of tells us how to steer along a path. Right? If we're walking along at unit speed, the curvature is telling us how quickly should we be turning our steering wheel to the left or to the right. Right, so here's a little visualization. If I just hand you the curvature function kappa of s, then I could kind of replay this curve by walking forward at unit speed. And if the curvature is positive, in this case, I'm going to turn left. And if the curvature is negative, I'm going to turn right. And you can see in this example, places where I have very large spikes in curvature are places where I'm making a really rapid turn. Places where I have curvatures close to zero are places I'm going pretty much straight. The only information I'm missing here is, well, where do I start? Where do I start walking? And also, what's my initial direction? Right? Where am I heading when I start walking? So that's why the curvature doesn't completely determine the curve, but only up to translations and rotations. The other really important thing to emphasize is that this theorem really does apply only to arc-length parameterized curves, right? This is saying, okay, kappa is going to tell me how to steer my vehicle if I'm traveling at unit speed. If I do the same steering motions, but I suddenly speed up or I suddenly slow down, I'm going to trace out a different path through space. Okay, so a more general version of this fundamental theorem might say that up to rigid motions, a plane curve is determined by its curvature and its parameterization. That's kind of what we've been getting at all along. Parameterized curves really encode both shape and speed. Okay? So how would we actually do this? Let's say that somebody gave us the curvature function for an arc length parameterized curve, so we really know we are definitely traveling at unit speed. How then could we recover the curve from this information? Well, what we kind of want to do is sort of invert the two relationships that say curvature is the derivative of the angle of the curve, the angle made by the tangent, and the tangent is in turn the derivative of the curve itself. So what's the opposite of differentiation? It's integration. So we could say that the angle at any point s along the curve is, well, we just integrate from 0 to s the total curvature over that interval. Okay, so we find the cumulative curvature. The cumulative curvature is the total amount we turned, or the current angle. If we know the current angle of the unit tangent, it's very easy to get the tangent vector. Right? T of s is just cosine s sine s. And now we have essentially the velocity of the curve. We have this unit velocity vector. So if we want to recover the curve itself, well, we just integrate up those velocities. You can imagine we start at the beginning of time and we move in that direction at that speed. So gamma of s is equal to the integral from 0 to the current time s of t of t dt. Okay, so interestingly enough, it seems we have a procedure that recovers a curve with a given curvature, but it gave us one particular unique curve, right? What happened to that rigid motion? What determined the translation and the rotation of this curve? Well, hopefully if you were paying attention in calculus class, you know there are these constants of integration. Right? When I integrate, I should add plus c. In this case, we have two integrals, and the constants, well, the constant for the first integral is just some initial angle, let's say theta naught, that determines the rotation. The constant for the second integral is some initial position, let's say gamma naught, that determines the translation, where we start walking from. Okay. Here's a concrete example. Let's say we're given the curvature function kappa of s equals 1. So at every point of our curve, we have curvature 1. Think in your head for a moment, what do I think this curve looks like? Right? I'm assuming it's a arc length parameterized curve. Okay, and maybe you already know what this is going to be, but let's go ahead and do the calculation. So the angle theta at any point s is I integrate from 0 to s the curvature, which in this case is just 1. That gives me s, right? So the angle at s is equal to s. The unit tangent at s is then cosine of theta of s, sine theta of s. Well, those are just both equal to s, so we have cosine s, sine s. Okay? And so then gamma is the integral of the tangent from 0 to s, which is the integral of cosine t, sine t, dt. Okay? If you remember some basic calculus, you know that that is equal to actually sine of s and 1 minus cosine of s. So if we plot this curve, it's a circle, maybe not quite the one you imagined, right? It's been translated away from the origin, and we're starting at a kind of non-standard place. Okay, but you probably had a good sense of what the curve looked like, that it was circular just from the description of its curvature. In fact, this is a really important idea in differential geometry, that curvature gives you this really nice coordinate invariant description of shape. Right? It doesn't matter that the circle starts at a certain point or is oriented in a certain way. If you really want to understand the geometry of the curve, it's all about the curvature. It's all about the fact that it bends the same amount everywhere. Okay? I should also say that in general, it's very hard to do this kind of recovery from curvature analytically. In fact, I can only think of a couple very special curvature functions that can be analytically integrated, and even in that case, the final curve ends up using some pretty esoteric special functions. Okay, so this is not something you're going to do a lot in practice. However, it is very easy in the discrete case, given curvature, to recover the curve. So as we start to talk more about discrete geometry and algorithms, we're going to see that this idea of recovering geometry from curvature is a very powerful perspective and very powerful tool to have at your disposal. Okay, so beyond this fundamental theorem and the idea that you can recover a curve from curvature, what are some other really interesting things we can observe about curves? Well, one idea is this idea of turning and winding numbers. So if we have a closed and regular curve in the plane, then the turning number, k, is the number of counterclockwise turns made by the tangent as we go around the curve once. So for instance, if we have our usual circle, we'd say the turning number is +1 because if we start with a tangent at some point and we travel around the curve, that tangent has to experience a full rotation as we go from the beginning to the end. Similarly, if we have a curve like this, it has a turning number of +2 because the tangent has to turn around twice or 3 times or whatever. We can also consider a curve that's oppositely oriented, right? The same circle but going the other direction. In this case, the turning number is -1 because the tangent experiences, well, a clockwise rotation as we go around the curve. Right? Likewise, if we change the orientation on these other two curves, we get a turning number of -2 and -3. So here's an interesting question. We have turning numbers of +1, +2, +3, -1, -2, -3. And you can imagine going further with each of these. Can you have a turning number equal to 0? Right? Is it possible for the tangent to not turn around at all as we go around the curve? Maybe a good moment to pause the video, see if you can try to draw one. Right? Can that happen? Well, actually it turns out that it can. So here is a curve with turning number 0. Why is it turning number 0? Well, just think about sliding a tangent along this curve. How many turns does it make? Can you visualize that, or can you draw that in some way? A nice exercise. Okay. Another thing to think about is I claim that the turning number k is the total curvature of the curve divided by 2 pi. In other words, if we integrate the curvature over the whole curve and then divide by 2 pi, we should get k. Why is that true? We've seen lots of different definitions of curvature. One of those definitions will make this fact very, very easy to establish. So, good thing to think about. A different but closely related concept is the winding number. So the winding number n of a curve is the number of times the curve intuitively goes around a particular point P. So we have some examples down here at the bottom. We can see that for n equals 0, the curve doesn't really go around the point. You could imagine pushing the curve far away from the point. It doesn't get stuck on it. The next curve has winding number 1. So in some sense, it winds around the point once. The next curve winds around the point 3 times. The next curve winds around it -3 times because, well, the orientation is opposite. But what do we mean exactly? How can we make this more precise? So there are a number of ways you can give a precise definition to the winding number. One of them is to say that it is the total signed length of the projection of the curve onto a unit circle around the given point. Okay, so you can imagine taking, for instance, the curve at the left and squishing it down until it hits that dashed circle, or expanding it up until it hits that dashed circle. Okay, so now it's a curve that just runs only along the circle. And now you can imagine pulling it as tight as possible while staying on the circle. For some of these, it actually has to wind around the circle once or 3 times. For the one on the left, you can imagine actually scrunching up the whole curve to a single point on that dashed circle. right? It doesn't get stuck on that point. Okay? So these two concepts sound very similar. How exactly are they related? Well, here's one way to think about it. So we can think of the unit tangent of any curve as a map to the unit circle. So normally we've been drawing tangents as little arrows along the curve, but you could also draw the tangent as a curve where you take your pen and you kind of move it back and forth along the circle according to the angle of the tangent. The turning number is then the so-called topological degree of this map, just the number of times it covers the circle as we go once around the curve. Right? So if t of s is our usual unit tangent, gamma prime of s divided by the norm of gamma prime of s, then k is the degree of this mapping to the circle. Similarly, for the winding number, we could think about the map, which I'll call gamma hat sub p, obtained by projecting the curve onto the circle around p. Okay, we could write that like this. We do gamma at s minus p divided by the norm of gamma at s minus p. That's always going to be a unit vector, so we can think of it as a point on the unit circle. Right? The winding number is then the topological degree of this map. How many times does gamma hat go around the circle? Okay, so again, these sound similar, but it's clear they're different. One involves the tangent, one involves the curve itself. Here's an illustration that hopefully makes the distinction clear. So we have this blue curve, gamma, and we're going to walk around it. And as we walk around it, we have the white point, the point on the curve, and the black arrow sticking out of that point, the unit tangent to the curve. We can take that same data and draw it on the unit circle in the middle. Okay? And so the tangent becomes this kind of clock hand that goes around. The white point becomes, well, just a point on the circle that moves around. And what do you notice? So you might notice that as you go around the curve once, the clock hand keeps passing the white point. Right? So the tangent is making more revolutions around the circle than the white point, the projected curve. What that tells us is the turning number for this curve is bigger than the winding number for this curve. In general, there's no reason why these numbers n and k have to be the same. Right? They tell you different things about the curve. However, there is a very direct relationship between the winding number and the turning number. Do you see what it is? So one way we could have defined the turning number is we could have said, oh, the turning number is the winding number of the map T. If we forget that T comes from the tangent of a curve and just think of T as a curve itself, right? Then the winding number of T is the same as the turning number. It's just the number of times T goes around the circle. Okay, so hopefully that language is clear, and we can use it to talk about another very important theorem about curves, which is the Whitney-Graustein Theorem. So first we need just one more concept, which is the idea of regular homotopy. So to be informal about this, I'll just say a regular homotopy between two curves is just a motion where the curve always remains regular. Right? I deform one curve into another by a family of parameterizations where at no moment does the differential ever vanish. I always have well-defined tangents. Okay, tangent never goes to zero. So what does Whitney-Graustein say? It says, well, two curves have the same turning number k if and only if they are regularly homotopic. Okay, so this theorem is kind of obvious in one direction. If I deform a curve without doing anything funky to its tangent, right, the tangent never goes to zero, then I'm going to preserve the turning number. Maybe you could think about that on the unit circle, right? Think about that map T on the unit circle. How could I ever make T wind more or fewer times around the circle without actually breaking the curve somehow, doing something discontinuous? Okay. The other direction is a little trickier. How do I know that If I have the same turning number, I can necessarily find this nice regular motion between the two curves. And there are a variety of ways to prove that. I think one interesting way to look at this is to talk about a special case of the circle. So a corollary to Whitney-Graustein is that there's no way to turn the circle inside out. If I give you the circle with positive orientation and the circle with negative orientation, then there's no way to deform one into another, to flip the orientation by a continuous deformation of the curve. Okay? To get a feel for why this is true, well, we can just start playing around with various motions. So we could start with a circle and try to just slide all the points that are positive on the x-axis to their mirror image on the negative part of the x-axis. So something like this, right? And you notice there's this key moment, this critical moment in the middle where the whole curve is just on the y-axis. And if you look at the little arrows at the top, the tangents, you notice they suddenly flip. There's this discontinuous jump in the tangents. And so what that tells you is kind of the differential of that map had to pass through 0 to change sign at that moment. Okay, so this is not a regular motion. You have this sharp crease in the curve. But this is not the only motion we could consider. Okay, we could try moving different parts of the curve faster or slower. So maybe we move the middle faster than the top and bottom. Okay, but still, we still have these little places where the curve gets pinched and the tangent has to suddenly jump. Right? We're doing something discontinuous in the tangent map. And you can keep trying and try different motions, but no matter what you cook up, there's always going to be these moments where the curve has a sharp cusp. Right? And you know that well because of Whitney-Graustein. I haven't proven this theorem, but if you believe this theorem, you should definitely believe the corollary. There's no way to turn the circle inside out. Of course, you could just lift the circle up out of the plane and flip it over and put it back down. That would reverse the orientation. Okay? But this theorem is really about curves in the plane, curves that remain in the plane. If you want a proof of this theorem, there are lots of nice versions of it. One particularly fun one is this movie made by Nelson Max in 1972. It's one of the very earliest examples of computer graphics and mathematical visualization, but actually does a beautiful job of illustrating this proof. So it really walks through it step by step. And I'd encourage you to go find this movie. It's available in a number of places online if you're interested in really seeing why this theorem is true. Why is this Whitney-Graustein theorem interesting or helpful? Well, one reason is that it allows us to kind of put things into a canonical configuration where analysis becomes easier. Okay? So one really cool example of this is an important theorem about hexahedral meshing. So hexahedral meshing is the problem of breaking up some three-dimensional volumetric shape into little sort of cubes for simulation. Now, I should say these are not exact perfect geometric cubes, but rather topological cubes. They have 8 vertices, they have 6 faces, they're connected up in the usual way. Okay? And one question you can ask, really fundamental question is, well, when can I mesh up a shape in this way? So for instance, suppose I give you not a mesh of cubes, but I just give you the boundary mesh made of little squares, or really topological squares, quadrilaterals. Then there's this theorem from Thurston and from Mitchell that says a genus 0 quadrilateral mesh, meaning a mesh that is topologically the same as a sphere, is the boundary of a hexahedral mesh if and only if it has an even number of faces. So that's really nice. As long as I just count up the faces and it's 2n for some integer n, then I know I can find a compatible volumetric mesh. And that theorem sounds so simple, you think, well, surely there's a trivial proof of this. Like, surely this is not a deep fact. And indeed, in one direction, it's not that hard to show. So the really simple idea is, well, every individual hexahedron, little cube, has an even number of faces. And when I join 2 hexahedra together, I remove 2 faces, right? The 2 faces that meet get removed from the boundary of the union of those hexahedra. More generally, if I have one hexahedral mesh that has two n faces in it and another hexahedral mesh that has two m faces in it, then when I union them together, well, I'm going to subtract 2, or maybe if they meet at multiple faces, I'm going to subtract 2 times the number of faces where they meet. Okay? But I'm always going to go from an even number of boundary faces to an even number of boundary faces. Okay, so that was pretty easy, but what about the other direction? Right, so we now have this necessary condition. In order for a quad mesh to be meshable, it must have an even number of faces. But is it sufficient? If I come to you with any quad mesh with an even number of faces, can I be sure that it's compatible with some volumetric hexahedral mesh? Well, this direction is not nearly as easy, but here's at least a sketch of how this works. I won't go through everything in detail. So the first thing we need to think about to make this proof work is regular homotopy classes not in the plane, but rather on the sphere. Right, so we just got done with Whitney-Graustein that said that the regular homotopy classes in the plane are just determined by the turning number. Right, so two curves with the same turning number are regularly homotopic, and vice versa. In the sphere, actually, it's somehow simpler. So in the sphere, it actually turns out that every curve is regularly homotopic to either a little circle or a little figure 8. And the reason for this is that on the sphere, we kind of have moves that we can do that we couldn't do in the plane. So for example, let's say I start out with this little figure 8. I can actually stretch the curve out over kind of the back of the sphere and turn it into this curve that looks like it has turning number 2. Or at least if it were in the plane, it would have turning number 2. Right? And you can apply similar moves to turn any curve that looks like it has an even turning number into a little figure 8, and any curve that looks like it has an odd turning number into a curve that actually just looks like a little circle. Okay, so that's a nice fact. On the sphere, there are just two regular homotopy classes, these kind of even or odd curves. How do we use that to understand hexahedral meshing? Well, the idea is to say every quad mesh has associated with it a collection of dual curves. So what I mean by that is I could start with some quad, and then I start walking. I get to choose either north-south or east-west, and I trace out kind of a strip of quads on the surface. Eventually, because there are a finite number of quads on the surface, I'll eventually get back around and make a closed loop. Okay, so I have this, kind of funky closed loop here that wanders around the surface, or maybe I have a simpler closed loop that just goes around a small cycle of quads. And I can keep going. I can keep tracing out these curves until I've covered all of the quads in my mesh. Okay, so that gives me a collection of curves on the surface, and by this theorem that we just talked about, this kind of spherical Whitney-Graustein theorem, I know that I can always regularly deform these curves into just small figure 8s and small circles that are actually disjoint, right? So I could also just make them small enough so I can move them apart. Okay, so that's kind of neat. This dual network of curves is always the same in some sense as these little 8s and circles. Then to get my hex mesh, to prove that I can hex mesh this boundary, what I'm going to do is find a regular homotopy between my original curve network, the one that I traced through the quads, and this kind of canonical one where I have little 8s and little circles. And I can imagine that the way I do that is I actually shrink the sphere. So I start with my original quad mesh and I start shrinking it. As I shrink it, I follow this regular motion. I follow this regular homotopy to my circles and 8s. Okay. During that process, at any moment, I can stop and say, okay, well, every quad mesh defines this dual network of curves, and likewise, every dual network of curves defines a quad mesh. Why? Well, generically, right, these curves intersect pairwise. So at each point of intersection, I have this kind of degree 4 vertex in my curve network, and that corresponds to a quadrilateral in my quad mesh. Okay, so every time during this regular homotopy that these curves pass each other, I'm kind of defining a new quad mesh on my same spherical surface. To get my volumetric mesh, what I can do is I can sweep out this homotopy between these two different curve networks, and these surfaces that I sweep out are actually going to be dual in a similar sense to my hexahedral elements, right? Or at least after I do just a little bit more work. So I sweep out these surfaces under this regular homotopy. I maybe cap off the ends. I add other little widgets that I can do just locally. And I'll get a cell complex where if I connect up the center of cells as vertices, just like I do with the Poincare dual, then I recover a hexahedral mesh. Now, obviously, I'm omitting a lot of the details here. If you want a detailed version of this proof, it's nicely written up in this note by Erickson that you see at the bottom. One thing to say about this procedure is it's really useful not so much for doing practical meshing, but just to show a proof of existence, just to show this is possible. And the reason is that the mesh you get out of this is much, much bigger than kind of the optimal one. So this sweeping procedure can yield at worst order n squared hexahedra if n is the number of quads in the original boundary mesh, and you can show with further effort that you can actually do a lot better. You can have a hex mesh whose size is linear in the size of the boundary. This kind of analysis has also been generalized in various ways. For instance, Erickson shows that you can generalize to a boundary mesh of any genus. So if you have a mesh that describes a donut or some higher genus object, you have similar conditions. You still need that the number of quads in your mesh is even, right, by the same argument as before. But now you also have to think about non-trivial loops that can't be contracted to a point, and there's, again, conditions that have to do with homotopy of those loops. Okay, so the takeaway from all this is not that you should immediately understand all of this stuff about hex meshing, but rather to give a sense of why is something like regular homotopy and why is something like Whitney-Graustein a valuable tool. In this case, it's because it lets you reduce your analysis of the situation to just a couple very simple kinds of curves, these circles and these figure eights, right? So this continues with a trend that we keep mentioning in differential geometry, that often you make your life a whole lot easier by mapping or flowing or deforming something into a kind of canonical configuration. Once you have this canonical configuration, it's a lot simpler to understand what's going on. You don't have endless case analysis about all the zillions of things that can happen, right? You only have a small number of things to consider. Okay? Here's another interesting application of not turning numbers, but rather winding numbers. So remember, the winding number is the number of times a closed curve kind of wraps around a given point. And this is a useful piece of information to have in something like geometric computing, geometry processing, because it tells you when are you inside or outside of an object. If I want to know if I'm inside the object, or if I want to know if I'm at a point that's covered multiple times by an object, I could simply compute the winding number and get that information. There's a problem, however, which is that real data, scans and meshes generated by human beings, are not always perfect, right? We might have curves that don't exactly close. We might have meshes that have holes in them. And yet we still want to get a sense of whether we're inside or outside. Right? Just because we have a tiny hole in our mesh doesn't mean that there's not a reasonable definition of what it means to be inside or outside that mesh. So what we can do, because we understand the definition of the winding number pretty deeply, is we can say, okay, well, the definition said I just want to integrate or sum up the projected length of the curve onto a circle. And that's something I can still do even if the curve is not closed. I can still go ahead and compute that signed length. Okay, so for instance, if I have a circle that doesn't quite close, what's being plotted here is the projected length at each point in the plane. And you can see as the circle gets closer and closer to being closed, there's kind of less and less ambiguity about am I inside or outside. Right? So what I could do maybe is say I'll pick a threshold. If I'm above a certain value, I'm outside. If I'm below a certain value, I'm inside. This is something I can also do on surfaces rather than on curves. Let's say my surface is made of a bunch of triangles. Then at a given point, I could consider a little sphere around that point, little unit sphere, and ask for the total projected area of the surface onto that sphere. How do I do that? Well, I could just add up the projected areas of each individual triangle, and we get something similar. So if we have a nice closed mesh, then this unambiguously determines whether I'm inside or outside. But if my mesh has cracks or holes or other defects in it, I still get a number that captures pretty well at each point whether I might be inside or outside. And this idea of generalized winding numbers turns out to be very useful for a lot of practical tasks, like, well, extracting a watertight version of the mesh, maybe just by thresholding this function, by doing tetrahedral meshing, right? If I want to turn a surface mesh into a volume, I need to know which region of space is considered to be the volume. Or to do other operations like Booleans. I want to take the intersection or the union of two surfaces. How do I do that if the surfaces have cracks in them? Okay. Nice thing about this algorithm is it's very easy to implement. Let's consider the two-dimensional case. Let's say we have an edge, AB, right? And we want to compute the projected length onto a unit circle around a point P. Well, that length is the same as just the signed angle from A to B. Okay, so how do we compute that angle? Now this is just an exercise in vector calculus. So remember that the angle of a vector with components x and y is, well, it's kind of the arctangent of y over x. That's one way to think about that, but you have to be really careful here because the arctangent of a different vector, minus x minus y, will give the same angle. Right? There's this sign ambiguity. So what you really want to do in practice whenever extracting an angle from a vector is to use a two-argument arctangent function, which is often called atan2, okay, that takes the two separate components y and x and gives you the proper angle from the horizontal. In particular, if we want to get the angle for the generalized winding number, we can compute the vector a minus p, the vector b minus p, so u and v, and then the angle theta is just the two-argument arctangent of the cross product of these vectors and the dot product of these vectors, kind of the y and x component. So the cross product in 2D just meaning u1 v2 minus u2 v1, and the dot product is the usual dot product. Here's what that looks like. You could go ahead and do this at home if you like. So if I draw one segment, I get this kind of two-sided function, right? And as I start adding more and more edges to my curve, I get something that really starts to partition the plane into different regions of constant value. When the curve finally closes, I actually get the true winding number for this curve at each point. And in the meantime, I get something that's a pretty good approximation of what the winding number would be if the curve were closed. Okay? So you get a sense, these ideas of winding numbers and turning numbers and regular homotopy, super useful for applications in geometric computing. Okay, so far we've been talking just about curves in the two-dimensional plane. Let's talk about curves in three-dimensional space. So in particular, we'll say a parameterized space curve is a map taking each point in an interval 0L of the real line to some point in R3. So this is exactly the same as our definition for plane curves, except that now we're taking values in three-dimensional space. As before, we could put further restrictions on this map. We could ask that it be continuous or differentiable or smooth, and again, we'll just assume it's as differentiable as needed. The differential of this curve, just as before, takes vectors on the domain to vectors in the image. Okay, but again, we're going now into R3 rather than R2. So if I have this vector x of s, then d gamma of x of s is this tangent vector sticking out of the point gamma of s. And the differential is again telling us how that vector got stretched out as we went from the interval into space. Okay. More explicitly, let's say we want to map a vector field or just a vector x on R to the stretched out vector in space. How would we do that? How would we carry out that computation? Well, this is just a basic exercise in differentiating vector-valued quantities. So if we have our map gamma described as three scalar components, x, y, z, and our vector field x is just some scalar function a times the unit vector field partial s. Then d gamma is just the partial derivatives of those three coordinate functions times ds, the kind of basis 1 form along the interval. And d gamma of x is, well, we plug the vector field x into the basis 1 form ds. What does ds do? It measures the magnitude of its argument along the direction s. So it's just going to give us a. And so the stretched out vector field, the push forward of this vector field onto the curve in space, is just at each point a of s times partial x, partial s, partial y, partial s, partial z of s at s. Okay? A good analogy here, if you're totally lost, is we're just talking about the Jacobian. We're just saying that the Jacobian of the map gamma tells us how to take a vector on the domain and push it forward to a vector on the image. Okay? For plane curves, we said that curvature was a fundamental quantity. What about space curves? Right, so for plane curves, curvature captured the notion of how quickly the curve is bending. For a space curve, we also have a quantity called torsion, which captures how quickly the curve is twisting. Okay, this can take a moment to get your head around. What does it mean, bending versus twisting? So the intuition is that torsion is kind of out-of-plane bending. I like this example. If you imagine you have a little toy that's made of kind of plastic hemicircles that can rotate around, right? So each of these colored pieces is rigid but can rotate around each other. Then each piece is a circular arc. It has some constant curvature, right? And each piece on its own has no torsion. It sits entirely in one plane. But there is some torsion where these pieces meet, right? Where white meets blue, I suddenly twist myself out of the plane of the previous arc. Okay? A more kind of continuous example is this. So I have a curve of increasing torsion. It starts out just going around and around in the plane. And then I say, actually, why don't you also move up a little bit as you go around and around? So as we go up faster, we're increasing the torsion of the curve. Another way to think about curvature and torsion is in terms of a frame adapted to the curve. So each point of a space curve gamma has a natural coordinate frame on it called the Frenet frame, which depends only on the local geometry. This is nice. Every curve that you've ever seen, right, your hair, the cables connected to your computer, whatever it is, even though you can't see it, it has this canonical little frame associated with it. So what does this frame look like? Well, as in the plane, the tangent is found just by differentiating the curve. Okay? And then if we differentiate the unit tangent, so we normalize t and then differentiate it, then we get the curvature times the unit normal n. Okay? So t is dds of gamma if it's arc length parameterized, and n is dds of t divided by the norm of dds of t. The frame is completed by the so-called binormal, which is just the cross product of t and n. So t and n are orthogonal, they're unit, and so b is going to complete an orthonormal frame. One way to think about curvature and torsion is that they kind of describe the way this frame changes as we move along the curve. So if we differentiate the Frenet frame in time, or in the arc length parameter s, we get this equation that says the change in the tangent and the normal and the binormal is, well, we take this little matrix and we multiply it by the current tangent, normal, and binormal. This matrix has two constants in it, kappa and tau, the curvature and the torsion. Okay, and you'll see in your reading exactly why this is true. This is basically just a straightforward application of properties of orthonormal matrices. Most importantly, this equation tells us that the change in the tangent describes bending or curvature, and the change in the binormal describes twisting or torsion. Right, we can see that from the first row of the matrix and the last row, respectively. Right, so the first row says the change in the tangent is equal to minus the curvature times the normal. Or if we want to kind of extract the curvature, we could say, oh, well, that means the curvature is the inner product of the normal with the change in the tangent, right? Because dds of t is kappa t inner product of n with itself is 1. Okay. Likewise, we can write the tangent as the inner product of the unit normal with the change in the binormal. To give a little more concrete example, let's consider the Frenet frame of a helix. Okay, so we have a helix gamma of s, which is equal to a cos s, a sine s, bs. Right, so if b was 0, this would just be a circle in the plane with radius a. If a was 0, this would be a curve that's just moving straight up in the z direction. And to keep things simple, we're going to assume that we've picked a and b such that a squared plus b squared is equal to 1. We can always apply a normalization so that this is true. Okay? So what does the frame of this curve look like? Well, let's first compute the tangent. So the derivative of gamma with respect to s is minus a sine s, a cosine s, b. We need to still normalize this derivative to get the unit tangent. So the norm of dds of gamma is the square root of a squared plus b squared. But hey, conveniently, we've picked a and b so that that's equal to 1. And so in fact, this is already an arc length parameterized curve. The tangent is just dds of gamma. Okay. Then we can take the derivative of the tangent to get the curvature times the normal. Right, so dds of t of s is equal to minus a cosine s sine s 0. So if we visualize the tangent as points on the unit sphere, kind of like what we did for the turning number and the winding number, right? We see the tangent itself is just going around in a circle on the sphere. And the radius of that circle is a. It sits at a height b. Okay? The curvature is therefore minus a. Why? Well, again, we said the change in the tangent is the curvature times the unit normal. Okay? So cosine of s, sine of s, 0 is a unit vector, so that must mean that minus a is the curvature. And n is given by just this, well, this unit vector, cosine s, sine s, 0. Okay, so far so good. What about the binormal? This one's perhaps the easiest. We just had to take the cross product of the tangent and the normal, and we get minus b sine s, b cosine s, minus a. If we want to get the torsion, we take the derivative of the binormal, and that gives us dds of b of s is equal to minus b cosine s sine s 0. So what we learn is that the torsion is just this leading coefficient minus b, just like we did for the curvature. Okay, so the helix is a really nice example because with a helix, the curvature is just a, how fast are we going around this circle, and the torsion is b, how fast are we going out of the plane, right? At least if we've done this normalization. But that hopefully gives you some intuition for the meaning of curvature and torsion. Curvature is in-plane bending, torsion is out-of-plane twisting, or really out-of-plane bending. Right? They're both kind of a type of bending. So for planar curves, we said that the curvature completely determines the curve. It was a nice fact. As long as we know the curvature and we know that this is a unit speed curve, we can just walk at unit speed and let the curvature steer us as we go. The fundamental theorem of space curves says something very similar. It says we can also go from our curvature and torsion to a description of the curve itself, again, up to rigid motions, up to translations and rotations. Right? So the intuition is exactly the same. The curvature and torsion tell us how to steer, but now we're no longer just in a car or on a bicycle. Maybe we're in an airplane. Right? So we have different ways we can steer. We can roll and we can yaw, right? Not just turn our single steering wheel. In 2D, it was pretty easy to recover the curve from the curvature, at least conceptually. We integrate up the curvature to get the angle. The angle describes the unit tangent. We integrate up the unit tangent to get the curve. In 3D, things get slightly more complicated because we have this interplay between curvature and torsion and these three directions, n, t, and b. Right? We have this Frenet equation. And what this equation is a family of three coupled ordinary differential equations. So if you want to recover a curve from this curvature and torsion data, you have to integrate this system of ODEs. This is perhaps something you can do, again, for very simple curvature and torsion functions. I would bet that this works out for a helix. But in general, this is something where you really have to do numerical integration to hope you'll ever get a solution. Okay, and we'll see again in the discrete case, this becomes very straightforward. One last little question about the Frenet frame. So if our curve has a straight piece in it, is this Frenet frame well defined? What does it look like in this middle section of the curve? Well, the answer is no. The Frenet frame is not well defined in this straight piece because we don't have a well-defined normal or binormal. Right? The derivative of the tangent with respect to s is equal to 0. So we can no longer say that the normal is the change in the tangent, or we could, but then the normal would just be 0 and the binormal would just be 0. Right? So that being said, there are still many ways to choose an adapted frame. So an adapted frame means any orthonormal frame that includes the tangent. For instance, one way we might fill in the frame in this region is to say, give me the smoothest frame. Give me the frame that changes the least as I go from the last moment where I knew the frame to the next moment where I know the frame. It just twists slowly around that middle section. In fact, what some people like to do is just say, okay, I don't want to deal with this issue at all. I'm going to throw out the Frenet frame entirely and instead work with a different orthonormal frame called the Bishop frame. The Bishop frame is the frame that twists least along the whole curve. So you can imagine we pick just some initial frame at one endpoint and we try to slide it along the curve while twisting as little as possible. This is a nice idea conceptually. Computationally, it's not always the nicest thing because unlike the Frenet frame, this has a global rather than local definition. With the Frenet frame, if I want to know what it looks like at a point, and I'm not a straight segment, then I can just take local derivatives to get the three directions. If I'm working with the Bishop frame, then to know a point way down the curve, I have to do this kind of integration all the way to that point. Okay? But depending on what kind of application or algorithm or scenario you're in, these are different useful ways of framing the curve. In fact, this is kind of our first example of what's called moving frames. So there's a whole other language for talking about curves and surfaces, which we are just scratching the surface of, where it's all about putting a frame adapted to the surface and then measuring how this frame changes to get an idea of curvature and other properties of the geometry. Okay, to summarize, we introduced curves. We said there's many different ways to describe them. For instance, we have algebraic or implicit curves, but in differential geometry, the most common approach is to work with parameterized curves. Why is that a good approach? Well, it lets us express important local quantities via derivatives of the parameterization, like the tangent, the normal, the binormal, the whole Frenet frame. From there, we can take further derivatives to get the curvature and the torsion. We made a distinction between embedded curves and those that are merely immersed or regular. Right? So embedded curves were those that don't intersect themselves and kind of preserve the topology of the domain. Immersed curves can pass through themselves, but each little piece of the curve is still a nice, perfect segment that has a well-defined tangent, well-defined normals, and so forth. We also looked at the turning number and the winding number and saw some interesting applications of that to kind of geometry processing. And finally talked about the fundamental theorem, which says that you can always recover the geometry of a curve from its curvature or from its curvatures. So for space curve, you have curvature and torsion. And this kind of hints at a general principle. As you go up in dimension, you'll have multiple curvatures that describe a curve. And as you go to surfaces, which we'll talk about later on, you can also ask this question, can I recover the shape of a surface purely from its curvature? A lot of interesting stuff that we'll have to say there. Okay, but that's it for our introduction to curves. Thanks, and next time we'll talk about the discrete case.